How do I go to the next?
You either use that or.
Okay, yeah. Well, hello everybody. Thank you very much for coming. I'm Daniel Kreuter. I'm a first-year PhD student at the CMS here, and particularly at the blood counts project. And I'm going to be talking about investigating bias in full blood count data. So just to quickly remind you, if you don't know yet what a full blood count is, essentially when you go to the doctor and they take a tiny bit of blood of you, this is what they do. It's the most common medical laboratory test, and as such, it's essential for decision making, both in general practice as well as in hospital care. And the way it works essentially is you take a blood sample, you put it into a hematology analyzer machine, which itself is a flow cytometer, and it takes measurements of the cells in the blood, and it returns quite a lot of measurements. Around 20 of these are normally used in clinical use, but over 100 are actually reported by the machine. And as such, we at the blood counts project would like to use AI to harness this more rich full blood count data to make better medical decisions, as well as for early detection of new disease outbreaks. So then looking at full blood count data, we quickly noticed some problems though that everyone will be familiar with biases and dirty bits in the data. So here we see a blood donor study called Interval, and I just showed two examples here. On the left, you can see white blood cell count plotted over the delay between venipuncture in the patient to the acquisition into the hematology analyzer machine. So essentially, how long did you leave the blood lying around before putting it in the measurement machine? And we can see that this actually has quite a big impact on the measured result that we get reported back. So this is not part of the real signal, but this is a technical effect that we'd like to eliminate. Also, since we want to use a bit more of the richer full blood count data, this blood donor study actually used two hematology analyzer machines, which are quite well calibrated, or very well calibrated in the common numbers such as red blood cell count, white blood cell count. But in the richer data we want to use is actually quite a bit of discrepancy between distributions sometimes, and that's also, these are supposed to be machines that are identical, right? So it seems that our data is distorted by some domain background, which we have to somehow model and try to get out in order to make it comparable. And these background errors might be interacting as well. And what we noticed then is if we put this in some sort of embedding space using autoencoder, for example, we would first have clusters of the machines, and later by the actual classes we want to classify by. A way to solve this, which we've done, is using a general additive model. So a bunch of penalized spline terms essentially. And we can see that this corrects it quite well in the sense that the machines are no longer correlated. However, if you wanted to scale this up from 2 machines to maybe potentially thousands of machines worldwide, is how we would like the blood counts project to develop, then this no longer becomes feasible, because essentially this additive model you would have to rerun every time you add a new machine in order to keep it comparable. So ideally what we would like is a method that is as good at modeling these bias effects as the conventional methods, but also is scalable to thousands of domain backgrounds, and as such keeps being comparable and reproducible, so that if we use it in one hospital, we can immediately use it in the next one as well, which is often can be a problem with these AI methods, where the bias is just kind of learned within the model. And it should be adaptable in the sense that maybe we don't know all of the domain biases, but we would like to add more to them. We have developed such a method, and we're currently working on a manuscript to be shared in the coming months with the community. And by we, just quickly showing we're the blood counts team. These are just some of the faces you might see around this week even, and come talk to us if you like. And with that, I'd like to give over to Samuel Tull, who's going to talk a bit more about a direct application from full blood counts that we're also working on.
Very good introduction. But Samuel Tull, who's going to talk about can we predict the severity of COVID-19 using full blood counts?